Okay, here we go. So Anna said that the input into sine was the measure of the angle swept counterclockwise from the 3 o'clock position. What do you think about that? Audie, agree with that?
Yeah.
Do we need, so what about the unit for this measure of the angle? What's that?
In radians or radius lengths?
Radians or radius lengths. Is radius lengths an angle measure? That's a distance measure, right? That's a distance measure. So actually, the input into sine, it can be any angle, anything we measure angles with, as long as your calculator knows, if you're using a calculator, or you know in the context which unit of angle you're using. But it could be degrees, it could be radians, grads, sparkies, whatever, right? Anything we make up. But the key is, it's the measure of the angle swept counterclockwise from 3 o'clock. What is the output of sine? Diana? The vertical, she said the vertical distance above the horizontal diameter in radius lengths. What do you think? Exactly what it is. Okay? Again, to reiterate, we're going over this, you're taking the quiz on it, we're practicing it, because it's this understanding that allows you to solve the problems. It's this understanding that allows you to solve the problems. It's not just words to memorize, to get points on your grade. Okay? It's really knowing, this is really knowing about what sine is. What is this thing, sine? It's about knowing what the input is and what the output is. Okay, and then which coordinate on the circle is this correspond to? Yeah, this is the y coordinate, right? This is the y coordinate on the circle. Okay? Other half of the first page on your quiz, cosine. Let's do it again. So Christian, what's the input into cosine?
Same sign as the angle swept counterclockwise from the 3 o'clock position and any measure of an angle.
Okay. And just to be a little more nitpicky, it's the measure of the angle, right? So the angle is this object, but the input is a number. So we want the measure of the angle, okay? So that, just to make it perfect. And then what's the output, Taz?
The horizontal distance right
In radius lengths, right? The horizontal distance to the right of the vertical diameter in radius lengths. Coordinate? X coordinate, okay? So there's the first half of your quiz. There's the first half of your quiz this week. Second half, let's do it quick, is the unit circle. I gave you the exact sheet that you're going to fill out. So it all started with, oh, I don't want that, I want this. It all started with our integer wrapping the radius along, and then we saw that halfway required 3 radius lengths to get halfway around. And our radian angle measure comes from the number of radius lengths cut by the rays, right? So the radian angle measure of a straight angle or half a circle is pi. And so we could get, then, using pi, we can get these, what we call the 16 key angles, okay? Which are based on symmetry with the axes, right? Based on symmetry with the axes. So the first set would be the ones based on pi over 4. Okay? So pi over 4 is taking that half circle and breaking it up into 4 equal arc lengths. So that first angle there would be our pi over 4. So then to get the rest, all you got to do is know how to count. So there's that first one's 1 pi over 4. Then 1, 2, 3, 4, 5, 6, 7, 8. If you know where pi over 4 is, and you know that breaks the circle up into 8 equal pieces, you just count 1, 2, 3, 4, 5, 6, 7, 8. And we know the top, the left, the bottom, and the right, we already know those angles. So these are the new ones that we get when we count by pi over 4s. Okay, and we do the same thing with pi over 6. So we split up the half circle into 6 equal pieces. And so therefore that angle that cuts off 1/6 of half a circle is what angle? You're all thinking it, right? Pi over 6. So the angle that cuts off 1/6 of half of a circumference, that will have a measure of pi over 6 radians. Okay? Then we just count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 pi over 6 would be our 2 pi. Okay, once again, when we do that, sorry, try. Oh, back one. Once again, when we do that, we get the top, left, bottom, and right, which we already knew. Okay? But then we get these other 8 angles. And these, the ones toward the top and toward the bottom, then those simplify into our angles that end up having 3 in the denominator. So pi thirds. 2 pi over 3, pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Okay, so those simplify to our pi thirds. But you can just get them by counting the sixths, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way around. So what I'm trying to give you is a way to, you don't have to memorize this symbol goes in this location, this symbol goes in this location. Okay, so I'm just giving you, if you just know a couple things and you know how to count around, then you can just generate this really easily. Okay, and so it's all based on this. So because we picked these angles, because they're all based on symmetry, then the resulting sines and cosines all we need is we need those sines and cosines in the first quadrant, and then we can apply just the right positive or negative. Okay, so we said the x-coordinate was which? Cosine or sine? X-coordinate. That's our cosine. So where would the cosine be positive? So we got quadrants 1, 2, 3, and 4. In which quadrants is the cosine positive? Okay, most of you are saying 1 and 4. 1 and 4 is where that x-coordinate, or the cosine of the angle, will be a positive value. Why? Because we're measuring, cosine measures horizontal distance to the right. So when you're to the right, it's positive. When you're to the left of that y-axis, it's negative. What about sine, our y-coordinate? That's positive in 1 and 2, where the vertical distance is truly above the horizontal diameter. If it's below, we use a negative to denote how far below the horizontal diameter. Okay, so just real quick, what is the sine of 5 pi over 6? Corey, can you tell me the sine of 5 pi over 6? 1/2. You want one positive or negative? Positive 1/2. What do we think? Good. Okay. What is the cosine of 3 pi over 4? Cosine. Malin. Okay, so why negative? X-coordinate. Yeah. So we're to the left here. So the x-coordinate is going to be the same x-coordinate as pi over 4, but negative, right? So negative radical 2 over 2. Okay? Sine of 11 pi over 6. Con. Sine. Negative 1/2. Same sign as pi over 6, but sine is negative in the fourth quadrant because we're below the horizontal diameter. Okay, so again, all you need to know is, if you just got to know these coordinates, all right, and then you're going to apply all those same values to the rest here. It's just that you will need the right positive or negative sign. Okay, when you fill out that sheet, I got to find it real quick. Oh, no, it's this. So the blanks, so for the coordinates, these here, these coordinates, and for the radian coordinates, use that blank as the fraction bar. It just makes for a much cleaner result in the end. Okay, so for instance, this angle right here is, which one's this right here? Right, that would be our second pi over 6, right? 1 pi over 6, 2 pi over 6 would be pi over 3. So use that thing as the fraction bar. And then likewise here, use these as the fraction bar. So what is the cosine of pi over 3? Or the x coordinate? That's 1/2. Right? And you can, if you forget, you can just come down here and draw this thing and be like, okay, where am I? Oh yeah, that's 1/2, right? And then radical 3 over 2. So where it's appropriate, use the line that they give you as the fraction bar, because it makes for a much easier grading, okay, and just cleaner result when you're all done. You can ignore it down here at the bottom. It says positive, positive, so you can ignore that, okay? Just where it says positive, positive, just ignore that. You're filling in all the. Oh, and then we didn't talk about degrees. So here's our first quadrant. Radians, we know. So it's the same thing. So pi over 4 is how many degrees? 45 degrees. So again, you can just count and you just keep adding 45. So 45, add 1, so add 145. Add it again, add it again, add it again, until you get to 360. So you don't have to memorize. You can just keep adding 45 degrees. Same with pi over 6. How many degrees is pi over 6? 30. So now just as you counted pi over 6, you can just keep adding 30, add 30, add 30, add 30. Right? And then make sure, just as a reference, we should get to what angle now here? That's 180 when we add 30 around halfway. And then, boom, add 30, add 30, add 30. Keep adding 30. And then we'll end up at 360. Okay, so this week's quiz, you'll be working on that. Any questions? So let's go back to where are we going here? So look on page 275. So here's the scenario. We're twirling this ball around on a string. Okay? And it says that, it just say that the number is a number, what's the number that says it's going 2 radians per second? What number is that?
4.
Number 4. That's where we're going to start. So we're going to be turning, the ball is twirling at 2 radians per second. Okay? So here's something of what that looks like. Okay? And so what they want is, they want to know the angle in terms of time, right? They want a relationship that gives you the angle if you knew the time. So what is that saying? That's saying theta in terms of t. Theta in terms of t. Okay? So if you ever ask for something like that and you're not quite sure, so some of you may know that already based on what's going on, you may be able to just, you know it, but others may be like, well, I don't know. Well, set up a table of those two quantities and get some ordered pairs and see if you can see the pattern. So we're going to, for a given t, we're going to calculate some different thetas. And then based on the pattern that emerges, we can come up with what do we need to do to t to get theta. So if 0 seconds have gone by, what angle has been swept out? 0. Okay, after 1 second, how many radians have been swept out? 2. It's the definition of 2 radians per second. What does that mean? It means every second you sweep 2 radians. 2 radians per second. So what about after 5 seconds? And what about after 30 seconds? 60 radians. So now we begin to see the pattern emerging, and we can say, all right, if there were any time t, what would the corresponding number of radians swept out be? Brooke, what do you think? 2t. The number of radians is always twice the time elapsed because it's going 2 radians every second. So that means that for every, the angle is always twice as much as the time that's gone by. 2 radians per second. Okay, so that's that relationship that they're looking for. So this is a really important technique that you should be able to come up with. If you can't come up with this formula right off the bat, form a table of values and look for the pattern. It's a really crucial technique that you should think of. Okay, you should think to do that if you can't come up with that. Okay, so now we want to look at, so now I have this graph. And this axis is our normal axis, and I'm going to tell you that this right here is 2 pi. Okay, so what is my x-axis quantity here? If that's 2 pi right there, then what's implied as the x-axis quantity there? What quantity have I put on the x-axis? So they tell you, is this feet, or is this angle measure, or is it distance, or is it radius length, or arc length, or what is this? What's that? Radians. Okay, so this is angle measure. Okay, and if we were to have this function where that input was theta, so I'm not asking what the function is, but now I'm asking this blue graph. What quantity relative to the ball, is that blue graph showing us? So what quantity relative to the swinging ball is that graph showing us? Adi?
The cosine.
So no, but what quantity relative to the ball? So what quantity?
So it would be the horizontal distance to the right of the vertical diameter.
Okay, and I didn't give you a scale there. So if we're in radius lengths, then this would be 1. And this would be... So he said that blue graph is showing us the horizontal distance of the ball to the right of the vertical diameter. Agree with that? So therefore, what function is that? Like he said, that's a cosine. So obviously this, when you twirl a ball on a string, you're going to do more than one circle, right? So when the ball finishes one revolution and starts again, that's angles greater than 2 pi, right? So it's like the second circle would be angles from 2 pi to 4 pi. What would the graph look like? So if we kept drawing this graph starting at 2 pi out to 4 pi, similar? Exactly the same. It's going to cover the same profile of horizontal distances as it makes another loop, right? So the output values will be exactly the same, the exact same pattern from 2 pi to 4 pi, and then the next circle, the next circle, the next circle. So because of that, we call this one cycle. This is one cycle of output values. And as the angle keeps increasing, the ball just keeps going through the same cycle and cycle over and over again. So those horizontal distances keep repeating. Okay, so 2 pi is the interval of input that results, so that gives 1 full cycle of output values. So 2 pi is the interval of input that gives 1 full cycle of output values. And that's that's important. It's like how far do we have to go through the input until the output starts repeating again? So it's a really important thing. So it has a name, which some of you might know. What is this called? This interval of input such that we get a full cycle of output values.
Oscillation.
What's that?
Oscillation.
Oscillation? Period. That's the definition of the period. The interval of input that gives 1 full cycle of output. The interval of input that gives 1 full cycle of output values. And so what is the period of cosine? The cosine function, what is the period? 2 pi. It's really important because every other period that we calculate will be based on this, knowing that one full cycle of angle measure one full cycle of output values we get from 1 rotation or 2 pi radians. Okay, so that's the period. So now, what if we wanted to define the horizontal distance again, but now as a function of time? So now we want a new function that gives the same output values, but as a function of time instead. We'll call that g of t. I'll do all this in blue. So we still want the horizontal distance to the right of the vertical diameter in radius lengths, but as a function of time. Patrick, any ideas?
Would it just be cosine of 2t?
And why did you say that?
Because we want the same output, but the input needs to be t, and our theta is equal to 2t.
Well, do you hear that? That's perfect, what he said. So we still want the output to be the same thing, cosine, horizontal distances. But now if we want the input to be t and theta equals 2t, then it's just cosine 2t, because 2t is theta. So now we want to talk about the period of g, the period of g. So if the period is the interval of input that gives 1 full cycle of output values, then we're talking now, the period is a matter of t now, instead of theta. Okay, so we want to know what is the interval of time that will result in 1 full cycle of output. And so we get that from this fact that we know that the period of cosine is 2 pi. So this 2t represents, what quantity does that represent? 2t. That's our theta. And if we're interested now in theta, we need the interval of theta that gives 1 full cycle, which we know is 2 pi. So we want the specific value of t that's going to make theta equal to 2 pi. So we can just take our theta, which is 2t, and this is a specific value of t, the period, so I'm going to call it t sub p. And so this is what we're going to do to get the period of a function, knowing that this thing, the angle, needs to go through 2 pi. So we're asking what value of t is going to make 2t reach 2 pi. Should make sense. Does that make sense? And then what will that be? So now we're solving for the period. T of p is? Just divided by 2? Pi. So now what are the units on that? Pi what? Is it seconds? Or is it radians? It's a time, right? It's an input value. It's a time. It's seconds. So now if I were to do the same graph as the g function, then this scale would be different. Here, now at the full cycle, we'd be how many seconds? It'd be pi seconds, right? And how many seconds would it take to do half a cycle? Pi over 2. 1/4 of a cycle would be pi over 4. And 3/4 would be 3 pi over 4. So now that this blue scale is for the g function. If it was if we were measuring in terms of seconds, or using the g function. Okay, so the period is always, when you talk about the period of a function, that's always a question of truly the input of that function. But what we're going to use is we're going to use the whole expression going into cosine to allow us to do that, because we know that that's our angle measure. And to get a full cycle, that angle measure, the whole thing that goes into cosine, in this case 2t, for one cycle needs to reach 2 pi, because that's the period of cosine. So that's where that thing comes from right there. Okay, so how about this situation? Twirling a ball 2 radians per second. Any observations about that? So imagine you've got just a string, a couple feet long. We're going to twirl this ball. And this is 2 radians per second. Any comments? What does that mean? Let's see. 1,000. So the way that this ball is actually, the animation, the way I have it is pretty close to 2 radians per second. Any observations? What's that? Is it realistic? Anybody think they could do that? Audie?
I mean, if you had a long enough string so that the radius was...
But it's like 2.5 feet, right?
Yeah, so then, no, because it's
To what?
It'd be going too fast if it was contained in that small of a circle.
I'm asking about this. Is this realistic?
I don't know. Is there 40 feet between you and the end of the ball? Then it would be realistic.
But we have 2 feet of string. We have 2 feet of string. Jaden?
I don't know about you, but I can't swing a ball when it's not here at first. I can't define boundary.
What?
We can't start at 0.
So we get the ball swinging, and then we start the clock when it passes the 3 o'clock position. Okay, that's a fair point. Okay, so we're swinging the ball around, and then when it passes 3 o'clock position, we'll start the time. Okay, so that we can take care of.
It's too constant.
Too constant?
No one could swing a ball perfectly.
It's too slow. It's too slow. There's no way we could swing a ball this slow, right? And keep the string taut like that. There's no way. It's just way too slow. So let's do something more realistic.
Like 4 radians per second.
So we're going to do 9.7. So let's say twirl at 9.7 radians per second. So we want a function h of t that gives still the horizontal position of the ball to the right of the vertical diameter, t seconds after it passes, the ball passes the 3 o'clock position. And then I want the period. So give that a shot. See if you can come up with a function. And before you even do that, you might ask yourself, how am I going to find theta in terms of t? What is theta in terms of t first? And then what will this function be? And what will the period be for the h function? And I'm going to set that up, and we'll take a look at what that looks like. It should be more realistic here. That's more what it would be like if you were swinging a ball in a circle, right? Be something like that. Okay, so that we don't get dizzy or hypnotized. How would you define theta in terms of t? Tim, did you get that? So if it's going 9.7 radians every 1 second, how many radians does it go in t seconds? That's what we're asking. Right. So in 2 seconds, it's going to go twice 9.7. In 10 seconds, it's going to go 10 times 9.7, because every second it's going 9.7 radians. So what can we write for the function h? Nina?
It would be the cosine of 9.7 times t.
Okay, in that expression, in that rule for the function h, what does 9.7t represent? In that function, in that rule for h, what does 9.7t represent, Brian? Okay, what quantity is that? So, what quantity? That's right. So that when you look at that, since it's the whole thing going into cosine, it's the input of cosine. It's not the input of h, but it's still the input of cosine. So as a whole, that 9.7t is the angle swept counterclockwise from the 3 o'clock position, and that's how we said theta equals 9.7t. Alex?
Is there any reason why we're doing cosine and not sine?
It could be sine, yeah. It's just I had to pick one. We just had to pick one, yeah. Yeah, so we do this whole same conversation with sine, and we'd be talking about the vertical position of the ball above the horizontal diameter. Okay, so what's the process that we go through then? If 9.7t is our input into cosine, and we want 1 full cycle of output values, then we want that angle, 9.7t, to be what for 1 cycle? 2 pi. So the key is seeing that 9.7t, since it's the input into cosine, it's an angle measure swept counterclockwise from 3 o'clock. And so if we want 1 full cycle of cosine, that whole thing that goes into cosine needs to reach 2 pi. And so the value of t that makes that happen is what you get in order to make this equation true. So it's going to be 2 pi over 9.7, and let's get an approximation for that. It's about 0.6 something. 6 what? So let's say 6.5. What's the units on the 0.65? Is it feet, meters, radians, seconds? Seconds. It's a time. It's an input. So for the h graph, our period we said was, did you say 648? 777, so 648, okay? It's also seconds. So for the h graph, our full cycle occurs at 0.648 seconds. Again, we're going to, as we start analyzing and drawing these cosine and sine curves, they're always 4 parts, right? there's always based on the 4 quadrants. So we're going to take our period. We're going to start by dividing by. We can divide in half first, or divide by 4. Okay, so what do we get when we divide by 0.648 by 4? 0.1 what? 60? 62. So 1/4 of the period is 0.162, and then we got 0.324 would be this point. And then, so you can take 3/4 of your period, or you could add these two together. Both work, right? So you could take a half plus a quarter more, or you could take 3/4 of that, whatever you want to do. 486. So if we were graphing, if this blue graph represented h, the h function, then our x, or our horizontal axis scale would be the red scale, because we know it takes 0.648 seconds for the ball, a little bit more than half a second for the ball to get all the way around. Okay, anybody have a question on this? Now, so we're bringing a new variable into it. We're bringing time into it, and we're going to write these cosine and sine functions as functions of time. But the key is that you see there's the middleman of the angle. So this, whatever expression we're putting into cosine or sine as a whole is still the angle swept counterclockwise from the 3 o'clock position. Still the input of sine or the input of cosine. All right, so let's do next. I'm going a lot faster than the first class. Okay, so let's go back to this. So before we started with f, and we said the input of this function was theta. Then, this was our h function. Let me change it here. This is h of t now. H of t was that last one we did with the red. Now the input is t. But we saw that this thing, 9.7t as a unit, was important for us as we were doing this analysis. So it has a name. It's called the argument. Okay? So the argument is this, whatever this whole thing is that we're plugging into cosine. Okay? We're not mad at each other. Okay? It's not about conflict, right? It's just the name that they chose to mean what is this thing? Because we already used input. Input is what is the input into the function. So now there's this other input, that whole expression that's going into cosine. So now we'll call that the argument of cosine. Alex?
I think maybe the people are trying to decide what to call that term.
Okay.
Having an argument.
There you go. That's it, right? So they couldn't figure out what to say. So yeah, right. Excellent. I like it. Okay, so what quantity does the argument represent? What quantity does the argument represent? Austin, do you know? Which is? So practice for your quiz. What is the meaning of theta? Yes, that's it. So because that whole thing, that argument is the input into cosine, that's the measure of the angle swept counterclockwise from the 3 o'clock position on the circle. Okay, and what's the meaning of the period of the function? So, without looking at what you wrote from before, can you describe what the meaning of the period is? Justin, can you tell me what the period means? Do you remember? Okay, it relates to a full rotation. So the period, does it have to do with that? Is it a measure of the input or the argument or the output, first of all, the period? Is it a measure of input values, output values, or arguments? Yeah.
It's the output value, measuring the output.
It's measuring the output. Is period measuring the output? Nina, you agree?
No, I disagree. I think it's measuring the input after all of the outputs have been exhausted. One rotation of the output.
Okay, yes. It's an interval of input. Okay, the period is an interval of input. How much input we need to do what? Get one full cycle of output values. So the period is always an interval of input. So will it be, what will that be then? Time, angle measure, or horizontal distance? The period. It'd be time, because our input is time, okay? It's the interval of input values that results in a full cycle of output values. So in this case, it's a number of seconds, or whatever the time unit is. Okay, next week's quiz. Definition of period. Next week's quiz, definition of period. It's an interval of input that results in a full cycle of output. So I'm going to put T up there, and then so you get an idea of what we're looking for, and then let's go back to work. So here's a good definition for T. The time elapsed in minutes since a point on the Ferris wheel past the 3 o'clock position. So it's all going to be relative, right? If we're using cosine, it's all going to be relative to that 3 o'clock position. So the time since a point past 3 o'clock position. distance to the right of the vertical diameter, then what? What's the maximum? The maximum cosine is 1, that's way out the far right side. Every other value is a fraction of the radius. 0.5 or 0.8, 0.2. So it's just a cosine. Cosine is only going to give you a fraction of 1 radius. And when you get multiply by 0.8. Then it's, now you've blown that circle up into the full radius in meters. Still horizontal distance, but now meters. Right? So if you were at 0.5, cosine is 0.5, you're half the radius out. How many meters are you out? 28. 14. Okay, what is 3t? Nadine, did you get 3t?
It's 3 radius per minute.
3t, the whole quantity 3t. What is it? Here's the key. The whole quantity 3t means what? Right, which is what quantity? Which is what quantity?
Oh, the actual measured angle.
There we go. 3t is our input into cosine, and that's exactly what we've been working on, learning, right? What's always the input into cosine? To measure the angle, so counterclockwise from 3 o'clock. So now, what does that multiplier 3 mean? So if t is the number of minutes and 3t is the angle, then what is 3? Anna?
It's the number of radians per minute.
The number of radians per minute that the Ferris wheel turns. What do you think? That's it. Because if we have the number of minutes and 3t gives us the number of radians, then 3 must be how many radians is going every minute. This is called the radial speed. The radial speed. So it's a speed, but it's measuring radians per minute instead of distance units per minute. Okay, cosine 3t. Let's see, Jared, right here. Did you get what cosine 3t means? Horizontal distance, right of what?
The right of the wheel of the vertical diameter.
Right of the vertical diameter in?
Radius length.
Right, this is cosine, just by itself. So it will always be the horizontal distance right of the vertical diameter in radius length. $28. Alex. Radius length of the wheel. What do you think? In what? Good. And finally, what do we get when we multiply 28, that radius length, times the horizontal distance in radius lengths? Huda. Horizontal distance, right of vertical diameter in meters, she said. What do you think? That's what we worked on all last week, right? So we worked hard on that. The cosine measures it in radius lengths, or a fraction of a radius, right? All those values are going to be like 0.8, 0.2, negative 0.5. Then if we apply the radius, whatever our units of our radius is, in this case 28 meters, we're taking that fraction of 28, and it's giving us how many meters we are to the right, right? Think of cosine as taking a certain fraction of your radius, right? So it gives us meters. Okay, what's the input of the function? T. What's the output? Which one of these 6 is the output? The last one, 28 cosine, the horizontal distance right of the vertical diameter. Which of these is the argument? 3t. Right? The argument is always going to be the measure of the angle because it's always the input into cosine. What's the period of this function, or can you give me the process of finding the period? Jared, number 2. I want to find the period of this. How do I think about that? Okay, so we want to find the period of f. And so we find that by knowing what the period of cosine is. Just cosine by itself. What's the period of cosine? Walter, what's the period of cosine? 2 pi. So when this thing reaches 2 pi, we get 1 full cycle of output values. So how do we get, then, how are we going to get t? The value of t that gives us 1 full cycle. What are we going to do? And we're going to take that angle measure, right? That's the measure of the angle, so counterclockwise from 3 o'clock. We want it to reach what? We want that angle to reach 2 pi. And when it does, that will be the specific value of t that gives us 1 full cycle of output. So we got 2 pi over 3, and then what are the units on that? Meters, minutes, or radius lengths, or something else? And let's get an approximation for that. If I remember from this morning, 2.09? So practice, so this is the period, so practice the meaning of that both in terms of the Ferris wheel and in terms of input and output of f. So get a partner, talk about that 2.09 minutes. What does it mean in terms of the Ferris wheel? What does it mean in terms of input and output of this function f? Go. Go. So what is 2.09 when you're talking about the Ferris wheel? Shola. How long it takes for the Ferris wheel to make 1 complete rotation, he said. What do you think? Okay, what about in terms of input and output? Jonathan, 2.09. What does it mean for input and output of f? How about, is 2.09, is that an interval of input or is it an interval of output? Interval of input. So what interval of input is it? What does it give us relative to the output? So it's that, right? 2.09 is the interval of input that achieves what, Alex? Achieves 2 pi. It gives 2 pi as the output of f. It gives 2 pi for the argument. So this 2.09 minutes would make the argument 2 pi. But the period is the interval of input that we're relating all the way directly to the output. So what does it give us related to the output? Jared? Nope. Well, yeah, but as the period, as the interval of inputs from 0 to 2.09 minutes, gives us what about the output, Taz? No, but the period is not a specific input value. It's an interval of input, right? The period is this interval from 0 to 2.09 that does something special with the function. What does it do? Yeah.
Give you all outputs of one cycle.
Right. It gives you a full cycle of outputs. Right. It gives you all outputs of one cycle. So that length of time. So what some of you were saying was right. If you plug 2.09 in, you're going to get 28 for the output. You will get 28 for the output. But when you're talking about 2.09 as the period, you're talking about as the stretch of time, this duration of time that gives you one full cycle of output values. Okay, so now let's practice how, no calculators, but we're going to use all this information that we found out to make a sketch of this. So first of all, we found the period was what? 2.09. So here, I'll rewrite this here. So this is 1, 2. So the numbers on the scale are 0.5 there, and then this is 10, 20. Okay, so if the interval is 2.09 is right here. So if we want to kind of make a sketch of this, that's one full cycle. We want to break that cycle up into what? How many pieces? 4 pieces, quarters. So 2.09, we're going to take 2.09 divided by 4, and we're going to get about 0.52. And then we're going to divide it in half to get halfway, and we'll get 1.5-ish. And then we can take 3/4 of that, or we could add a quarter plus a half, and we'll get 1.57-ish. So we just broke up the one full period into 4 equal parts. Okay. The next thing we're going to look at is the output values. What's the maximum value of this function? 28, right? And where is that going to occur? So at what time will we be at this maximum at 28? At 0? We'll be there at 0 seconds, so we'll be there. And then back again when it completes one full rotation or one period, we'll start there again. What's the minimum? Negative 28. And when will we get that? When will we get the minimum of negative 28? Halfway. Where on the wheel is that? Where is the point on the wheel right here? Halfway. That we're going to get the minimum value of cosine. Top, left, right, or bottom? Top, left, right, or bottom? Left side of the wheel, right? Left side. Cosine is our horizontal distance. So its minimum is going to be at the left side of the wheel, and that happens right at pi, right? So 0, pi over 2, and pi. That's why it's halfway through the cycle, right? Halfway through the cycle. And when will it hit the midline? So it's going to go at a quarter circle. Boom. What's the cosine? 0 at the top of the circle, right? Horizontal distance. And then it's going to go way out to the left. That's here. And then when it hits the bottom of the circle, 0 again. So now, make a V, straight lines like this. V. No, we worked on it the whole class. The rate is negative and decreasing. And then the rate is negative and increasing, becoming less negative. And then the rate is increasing. And then the rate is decreasing. And then after 2.09 seconds, what's going to happen after that? It's going to do it again. So we could mark off quarters again. Okay, and we could just keep drawing cycles, right? So this first 2.09 seconds is the first cycle. So let's check our work here. Okay, so we nailed it. this is the idea of sketching these functions. You got to find the period, and you're going to split that up into 4 parts. Find your maximum and minimum, and then depending on what you're doing, cosine or sine, you've got to analyze in terms of, is it vertical position above horizontal diameter, or is it horizontal position? Well, we knew this was cosine, so it's horizontal position, so at time 0, boom, we're at our maximum horizontal position of 28 meters. And then after half a period, boom, we're at our minimum, negative 28. Okay, questions on sketching the graph? Okay, so yeah, you've got your graphing calculator, but you will be tested and assessed on your knowledge of being able to do this. Okay, so you can't just use that calculator as a crutch. You're going to have to know all the details, okay, and be able to sketch them yourself. So practice that. Don't resist the temptation to just plug it in and graph it. Okay, practice what we just did. We'll be doing that for the next week or so. All right, so here's another scenario. So here's a water wheel scenario. A water wheel makes a full rotation every 13 seconds. The radius of the wheel is 7.5 feet. And for whatever reason, this may not be realistic, but the bottom of the wheel is 2 feet above the surface of the water. So maybe it's a decorative thing, right? Water is falling over it and splashing into the water. Okay, whatever it is. But the bottom of the wheel is 2 feet above the surface. A point on the wheel starts at the 3 o'clock position and turns counterclockwise. What I've got here is 4 different scenarios where you're going to write a function based on they're giving you the input and the output, and you're going to write the corresponding function. So read carefully, understand what you're reading, and apply the stuff we've learned. You've got to think about this, okay? You've got to think. And what I'll do, we'll come around and check and see how you're doing. And just to give you warning, usually about 90% of the people do not get one correctly on the first try. Read very carefully, connect it to what we've learned. Okay, go. So you're writing a function for each of these. Don't go on to number 2 until you're sure number 1 is right. Write down your answers, your functions, and show us. Read carefully, know what you're reading, connect it to what we're doing. Who can get number 1 right on the first try? Nope, not even close. Sorry, but you're not alone. Is that your answer for number 1? Are you still working on it? Not sure. This Thursday? Yeah, I just forgot about it. I didn't mean to. I wasn't trying to. Yeah, so just change it to a week from Tuesday, and then 17. Or you can post yourself. Okay, who's got a response for number 1?
I have an answer, but it's not.
Oh,
Are we allowed to use?
if you thinking really hard about it, you probably haven't gotten it. No. I love question number 1. It sees who is reading and thinking. Yes, got it. You want me to check the others? Oh, actually no. So the 13 isn't right. So 13 is the number of radians in a second. That's how long a full rotation takes. No, what is the input? It tells you what the input is. That's what it is. Got it. Some people are getting it. Number 1. Gotta get number 1 right. Almost got it. You got number 1 right now. That's good. That's it. Yeah, you got it. So here's the temptation. You just grab all the numbers out of the thing and you throw it in a formula. If you're doing that, it's not right. You gotta think and connect it to what we're doing. What's the input? What's the input in number 1? The angle swept counterclockwise, but from the 3 o'clock position, right? What's the output? Vertical height of the point in radius lengths. What function is that? Sine theta. That's exactly what we've been hammering. The input is the angle swept counterclockwise from 3 o'clock. The output is vertical distance above the horizontal diameter in radius lengths. Sine theta. That's what sine theta is. So now we want the vertical height in feet as a function of measure of the angle. That's G. So input is theta. How are we going to get it, the vertical height in feet now? Yeah. 7.5. 7.5. Right? Because sine theta is like the fraction of the radius, right? You can think of sine theta as a fraction of the radius, and so it's what fraction of 7.5 are we above or below? We'll pick up 3 and 4 on Thursday. There is web work for Thursday and a short written assignment from the book. And then there will be another written assignment posted that's due next Tuesday.